Hi everybody, and welcome back to Geology 311, Stratigraphy and Basin Analysis. This is the lecture content for week 2. It's a relatively shorter lecture where we're going to be just kind of reviewing the basics of sediments and sedimentary rocks. We will be getting into more advanced stuff as the weeks go on, of course, but I think it's a good idea for any stratigraphy course to make sure we're all kind of starting at the basics. So we're going to be covering Chapter 3 in your Brookfield textbook this week. Looking at transport and deposition of sediments, clastic sediments, and different types of sedimentary rocks, and also looking, of course, at chemical and biochemical sediments and sedimentary rocks. So let's jump right in. And again, starting with the very basics, we're going to just introduce the concept of sediment. And I know if you've had lithology or if you've had sedimentology, these are things you've covered probably also in your intro courses. I know we cover them in Evolution of the Earth. But we're just going to kind of all start at the same page and do a quick review. So sediment is defined as any solid, fragmented material such as silt, sand, gravel, or any chemical precipitants and fossil fragments that can accumulate at the Earth's surface. These are going to be transported by a number of media, including wind, ice, and water, and it'll accumulate either through direct deposition or chemical precipitation, and in the case of biochemical sediments, the secretion of the organisms themselves. And really, sediment is what's forming that outer surface of our planet. This is what's on top of the crustal rocks. So if we think back to the significance of igneous rocks, metamorphic rocks, and sedimentary rocks, going all the way back to the very basics, igneous rocks, by understanding their composition and texture, tell you something about how that rock formed under what magmatic type of conditions. Metamorphic rocks tell you the deformational history of a region. And sedimentary rocks, though, are unique in the fact that they represent ancient environments at the Earth's surface. So while we can have a beach or a desert forming today, millions of years from now, those will be represented as sedimentary rocks, including, in many cases, the ecosystem or parts of the ecosystem that existed therein. Of course, we have different types of sediments, and the first type we're going to cover are clastic sediments, solid particles from pre-existing rocks. So you take a rock, any rock will do, and you crush it up into physical little pieces, and you have clastic sediment. These will move from the weathering profile of their source rock and then deposit it into some other site as solid particles. Now, they may change during that transport in shape and size, and possibly even some chemical alterations, but we're still picking up an object from one place and putting it somewhere else. So to look at how the parent rock has been modified during the weathering process and the transport process, how the deposition formed, and what kind of diagenetic processes happened after burial. So clastic sediments are very, very important. A majority of our sediments are clastic. And of course, we describe these sediments in terms of composition. So what kind of mineralogy do they have? What's the grain size? What's the sorting of the grains within a lithified rock? How rounded are they on average? Are there any depositional textures that might be of importance, or any diagenetic changes that reflect any of these factors? So these are the tools that we need to use to interpret all of these things from clastic sediments. Bioclastic sediments, our next group, are a little bit different. So in this case, these are precipitated by organisms themselves. So the chemical alterations that are happening where we go from a dissolved material to a chemical solid precipitant is done biologically. It's done by organisms themselves. However, these are very important. They show what organisms formed this sediment. So in other words, if you have a coquina that's made predominantly of bivalve shells, it tells you that those were made by bivalves. They also show what kind of what type of modification has happened during transport, nature of deposition, and diagenetic processes. So we still get some of that overlap from clastics. However, what types of organisms are making up our bioclastic sediments? The taxonomic composition. We need to keep in mind how that is going to influence grain shape, grain size, sorting, roundness, depositional textures, and diagenetic features. And there's an important reason for this, and that's that bioclastic rocks do not reflect their weathering source or the transport history. So if you think back to clastics, you start out with a source rock and it weathers and breaks. Your initial clasts are going to be immature, they're going to be angular, based mainly on like the cleavage planes or the fracture of that mineral itself. As it transports, it may become more rounded. Well, when you look at bioclastic sediments, they may be rounded from their initial fracturing because that may be how the organism grew it in the first place. So we have different shapes and sizes, not because of a weathering profile or a weathering history, but because of the biology. So we have to be very careful when we're making interpretations like that with bioclastic sediments. Also, bioclastic sediments can undergo significant recrystallization and often replacement, which can cause some problems when you're trying to reconstruct depositional setting in history. For example, you can have carbonate particles from a wide variety of different processes, but they become aggregated, and now we can have either ooliths or grapestones or fecal pellets from certain organisms that are ingesting carbonate, and also broken rock fragments that are incorporated into this too. All of these are going to behave as detrital grains. All of them are going to behave in a similar way as clastic particles. However, the source of this tells a very different potential story. So bioclastics are very important, but we just need to know when to use certain tools when interpreting them. Finally, we get to our chemical sediments, which show the simple geochemical conditions that happen in water and where we get this precipitation. So this can include anywhere like lakes, groundwater, pore waters, anywhere in seas. And the composition of these rocks or sediments are really the only significant feature preserved because of the ease of recrystallization. So think about how easy it is to go from limestone to dolostone or so on. But in this case, you're taking a material, you're dissolving it into a solution. That solution is transported and it is then reprecipitated out, recrystallized elsewhere. And since we're talking about transport, let's look a little more at transport and deposition. So the transportation of any kind of sediment is going to be essentially driven by gravity, whether it's tumbling, rolling, or being moved by water. Deposition, on the other hand, if you really think about what causes a grain to deposit, this is driven by any chemical or physical change in the depositing medium. So for example, with clastic sediments, they can be incorporated into, let's say, a stream, and you've got momentum built up as that grain is tumbling downstream. It's going to deposit when the grain loses momentum and slows down, or when the competence of that transport medium, in other words, the velocity of our stream, decreases. In either case, there's a change in the depositing medium. For bioclastic sediments, we get deposits that are initially when that organism secretes the material. And then later, these fragments end up behaving as clastic particles. So the incipient formation of the grain is caused when the organism is alive. And then it's deposited later as a clastic particle. And our chemical sediments can be whenever that transport solution has reached saturation. So maybe from oversaturation from adding, let's say, lots and lots of carbonate to the water, or from evaporating water, thus making the solution more concentrated. In other words, once you hit saturation, you start getting precipitation. So figure 3.2 from your Brookfield textbook shows a Hilston's diagram that demonstrates the critical velocity of quartz grains on a plane bed. So we have to be very specific about these parameters. This isn't going to be a natural setting. So on a planar bed, let's say like a glass surface, quartz grains of various sizes and at different velocities. And you'll see we have our kind of transport area, our erosional area, and then our band in between. Where notice that clays and silts usually require a much higher velocity initially, and that's because they have such strong cohesiveness. You have to break those apart. Once they break apart, it's what we would expect, that the larger the grain size, the higher the velocity, whether in centimeters or feet per second, whichever you prefer, increases in order for deposition. Anything that falls below our gray band there of transport is going to be deposited. Notice erosion. To initially move this object, it requires a little bit more energy, and then to keep it going, you can have it a little bit lower. But if you fall below that gray band, that's when uh, you're going to start seeing deposition. Also want to point out this diagram also is in 1 meter of water depth. Again, another important parameter, water depth and what kind of planar bed you have or what kind of bedding surface you have. Let's discuss our clastic sediments and how we get sedimentary rocks out of those. Most of our clastic sediments are going to be transported and deposited by water and wind, though ice does play a significant role at certain locations, especially certain latitudes. But when we consider the maturity of our clastic sediments, remember this is something that we don't really factor in as much when we're looking at chemical sediments and to a lesser extent biochemical. Maturity deals with how much modification a grain has undergone from its initial source from the parent rock. So immature sediments are going to be the least modified, matured sediments obviously the most or more modified. Immature sediments are going to have a wide variety of different grain sizes and grain shapes. We can have angular to poorly rounded mixture of different rock fragments and different minerals. There's really not a lot of sorting going on. Even those that are easily broken down and physically or chemically weathered. So your immature sediments are going to break off of their source rock and get deposited relatively shortly after, both in duration and in distance. Mature sediments, on the other hand, much more restricted range of grain sizes, and we're usually seeing things a lot more sorted, both in terms of rounding and size. And by the time we get to truly mature sediments, we've usually broken down a lot of those accessory minerals where all we're really left with usually is quartz and or various types of clay minerals. Now, we have two different varieties of clasts that we can refer to in terms of basins. Extraclasts are grains or clastic fragments that are derived from outside of a depositional basin. So these are what are going to be transported in. Alternatively, our intraclasts are grains that are formed from within or derived from within the basin, maybe fracturing from rocks that are already in the basin, but often these include sediments that are sourced from soil nodules. So we have different types of clasts in terms of how we describe them with maturity, but also where that source material is. On page 24 of your textbook, you'll find figure 3.3, which goes over the maturity concept for clastics. One of the things I just really want to point out is the relative amount of kinetic energy needed to really start rounding grains. It needs to be relatively high before we start getting into really mature sediments. So the removal of clay and the sorting of non-clay portion of a sediment and then the rounding of grains all are really happening once we get into our moderate to high degrees of kinetic energy. So it's not easy to break down a quartz grain and round it. So when we find perfectly round quartz grains, for example, like what we see in the St. Peter sandstone, that's an incredible amount of energy that's been used on these grains over millions of years. Let's shift gears just a little bit for a moment, still in chapter 3, but looking at how we actually move sediment. We talk about clasts being incorporated into something like a fluvial system and being transported downstream or even blown around by air or by ice. But there's really quite a wide continuum of how we can transport clastic material. Anytime you have unconsolidated material that's moving, that's transport, and this can be as slow as what we see with soil creep, or we can start seeing mass flows, water flows, ice flows, stream flows, and so on. As you can see, going from mass flow and water flow, those are all parts of a continuum. And these also include debris avalanches, which we're going to talk about here in a little bit more detail. A lot of this has to do with the amount of transport medium we have compared to the amount of sediment that's in it. So the more sediment you have, you're going to see some very different types of behaviors regarding how that sediment is going to transport. A debris avalanche, for example, is a type of rapid debris flow, and extremely rapid, and this really doesn't have a significant amount of water involved with it. This was just a mass wasting event, a landslide, for example, where you're removing and transporting a significant amount of sediment very, very quickly usually with very steep angles, but this doesn't usually include a significant amount of water. This can just be a complete, rock failure where you get these kind of debris avalanches. And as you can notice, these are notable for the huge scoop that's been removed from, in this case, the side of a mountain, and then you can follow how everything has just flowed downhill. The Grovant rock slide is another good example of this out west. However, when we get to other kinds of debris flows, our more traditional forms of debris flows, these are also mass wasting events, rapid mass wasting events, but in this case we're looking at a combination of not just sediment, but rock, loose soil, lots of organic matter, but there's also air and water involved in this too. It's loose enough where you have some space and air in between some of these grains, and when you add water it turns into a slurry that just flows down slope incredibly fast. And then once it moves past its runout distance, what you see in the diagram here annotated as L, you have this large deposit of center mass at the base. These usually include a little bit less than 50% fine grained materials, so our silts and clays are relatively lower in these cases. And these are usually caused from really intense surface water flows. So you have heavy precipitation, you get a lot of rainfall, or a sudden early spring where you get a lot of snow melt and you've saturated that already unconsolidated sediment. This erodes and mobilizes all of that loose rock and soil, and in a very steep slope situation, you end up with some of these massive debris flows. In this example, we're going to be looking at hyperconcentrated flows, and these are really interesting. In this case, you have a lower sediment to water ratio. So you have differential and graded bedding, and some common places to see these are turbidity currents or turbidites. You're going to find these along the continental slopes and shelves down towards the abyssal plain, where these underwater currents, maybe an underwater landslide, causes a whole bunch of sediment to rush downslope very, very rapidly, but because it's in an aquatic environment, everything gets churned up. The weight of the sediment then starts to fall out of suspension in reverse order. So the heaviest material falls down to the bottom first, and then we get progressively fine grain moving up. So your turbidites or turbidity sequences are an example of a hyperconcentrated flow. Buma sequences also show this, and in the table EA, B, C, D, and E that you can see, we're seeing an example of one of these Buma sequences where you have graded medium to coarse sand above your organic marks, flute and tool marks. So we start out with coarse material. We then move up to parallel laminated fine and medium sands. We end up with cross-laminated silts, fine sands, our clay and silt, and then our organic clays, and we start the entire sequence all over again. So Buma sequences and turbidity flows or turbidity currents can produce very, very similar types of sequences. Notice also on the diagram that you see, both of these are from 3.12 on page 31 of your textbook. The diagram on the right, you can see how this also varies laterally depending on where you are in the basin. So these Buma sequences, again, if you're not familiar with that term, these are the kind of sequences we get from turbidity currents. Well, what about dilute water flow? These are the things we're a little bit more familiar with, probably. Your type of fluvial or aeolian deposits. The bed forms that we see here are really what we're going to be paying attention to. These are going to develop because of that interface, that interactivity between the fluid, whether it's air or water, and whatever the movable substrate of the bed is. And so you get bed materials that are modified by whatever type of fluid flow we have. So we have hummocky cross stratification, which produce these kind of smile-shaped cross-bedded structures that are caused from storms. Flasier bedding is more bidirectional bedding from intermittent flows, so you get alternating sand and mud layers. In this case, we do have a little bit more water than sediment, so the sediment is more able to kind of freely move around and develop these types of bed forms. So it's probably a good idea to review figure 316 and 317 on page 34 and 35 respectively, to be just kind of refresh your memory a little bit on some of these types of sedimentary structures and bed forms. And we have other types of flows as well. Ice flows are essentially glaciers. These are moving plastically. Ice is going to incorporate lots of unconsolidated materials such as tills, diamectites, and are going to deposit them upon melting, upon the ice itself melting. But they can produce a variety of other kind of bed forms, from shearing, crushing, and grooves, striations from the underside of that glacier having a frozen bed of sediments and grains that are then rolling and crushing over the landscape underneath. Our airflows or winds actually resemble dilute water flow deposits. If you think about aeolian deposits, they're more similar to what we see in fluvial settings than, let's say, Buma sequences, for example. So we have lower viscosity, lower density of the air, does limit the transport to pretty much granule-sized particles and smaller. We don't usually around this planet get winds powerful enough to be moving boulders or anything like that. So there are some differences, there are some limitations, but ultimately they're similar enough where we can make some educated comparisons. Once we've transported, well, first, once we've weathered, eroded, and transported our sediment, now it's time to deposit it. And once things are deposited, we have other changes that can happen. So let's look a little bit at post-depositional modifications. We have what we call our near-surface physical changes. These are going to happen pretty much immediately after deposition. So as soon as the clast falls into place, these are the types of changes we're going to see. And these include, but are not limited to, loading, in which case the denser sediment is going to sink into less dense sediment. So just because it lands doesn't mean it stays put. It can also work its way further down into a matrix of previously deposited sediment. You can get slumping, which is any kind of lateral or vertical movement of sediment after deposition. It's usually a large region or a pretty sizable region that's undergoing this. And of course, bioturbation, where any kind of trace fossils, where we have burrowing, scratches, tracks, any kind of biological modification or disruption of that depositional fabric is a type of bioturbation. And then once things have settled down on that aspect, we have actual diagenesis, which is a more deeper changes we're seeing both physically and chemically. These include compaction, cementation, and other forms of alteration. So compaction, where we've rearranged the grains into a dense configuration by removing fluids. If you take a handful of mud and you squeeze it and you open your hand and there's now a ball of mud inside your palm, you've just compacted sediment. You've rearranged grains and removed water. Cementation, on the other hand, involves precipitation of various types of cements, usually silica and calcite, though there are some other possibilities. And this is usually done through groundwater binding of grains during burial and compaction. So both of these are playing together at the same time in many cases. Other forms of alteration include the modification of grain composition, so authigenic growth of feldspars in sandstones or zircons, for example. These are all diagenetic changes that are going to happen during lithification, during actually taking loose sediment and turning it into a rock. I do want to point out that both near-surface physical changes and diagenesis overlap. It's not a linear set of processes. It's not like one happens and then the other. These are usually happening in tandem to some degree. So now that we have our sedimentary rocks, how do we classify these things? Well, as you hopefully are all already familiar with, at least to some degree, from taking previous courses, classification of sedimentary rocks can vary considerably from one classification system to the other. Ultimately, though, the goal of classifying is to provide some kind of name or category for these sedimentary rocks that give us some information about how they formed and where they formed. So, grain composition, for example. What are our sediments made of? This is controlled, of course, by the composition structure of the source rock. That usually doesn't change, though, as we just mentioned, authigenic mineralization is something to keep in mind. But we're going to quickly review a couple of tables from your textbook. Table 3.2, which deals with grain size, grain roundness, which is figure 3.31, other forms of grain shape, and sorting, which is 3.32. So all of these are things we want to include when we're talking specifically about clastic rocks, clastic sedimentary rocks, as a way of helping us classify these. So we're just going to kind of go through and review these diagrams briefly. I suggest following along in the book. Table 3.2 on page 42 of your textbook deals with sediment size, looking at our standard Wentworth grain size scale for our clastic sediments. Remember, this doesn't really work well with chemical sediments. Looking at it either in terms of micrometers or in millimeters, or even a phi scale. Your muds are going to be predominantly clays. Silts can be broken down into very fine all the way to coarse. Sands then from very fine sand to very coarse sand, and our gravel sized for the Wentworth scale going from granule, pebble, cobble, and boulder. Both of these, whether you're looking at the phi scale or the Wentworth class scale, both of these work together quite well. There's always a little bit of wiggle room in how we're classifying sediment. Ultimately, I always feel like your goal in the field should be to categorize them into silt, sand, or gravel in the field. And then once you get back into a lab setting, you can do a more detailed analysis under a scope to get a better idea of what kind of breakdown of a particle size analysis that you have. But remember, the size of the grain in the deposit is usually a reflection of some kind of change that has happened during deposition or to initiate deposition. Grain roundness, again, can vary quite a bit, even in terms of how we describe it. In this example, we're looking at angular, rounded, and very well rounded in A, B, and C, respectively. So river sand that's eroded off of a schist in part A, these are going to be angular grains. If you break a rock near its source, you're going to have angular, jagged grains. In B, though, we're looking at beach sands from a sandstone. These are moderately rounded grains. There's still some sharp edges here because we're dealing with wave action, and sometimes a grain gets deposited on a beach and it doesn't move again for a little while and then gets reincorporated. And then in C, our desert sands are going to usually very well-rounded grains, and they're also a bit frosted because they've been deposited in aeolian processes rather than fluvial. Water actually forms a bit of a lubricant in the way that our grains interact with each other, whether in a beach or in a fluvial system. But once you're in a desert situation, in aeolian systems, grains tend to, air also acts as a lubricant, but you've got smaller grains interacting with them, and so you end up with rather different types of grains. So keep in mind, if you're looking at very well-rounded grains from a fluvial system or even a coastal environment versus very well-rounded grains from an aeolian system, these can mean two very different things. Even beyond rounding, though, the actual geometrical shape of our grains plays a very important role in also how they're deposited and how they move. Whether we're looking at cylindrical or irregular, the different shapes of these are going to have different hydrodynamic properties or aerodynamic properties, if you will, which is going to affect how they move and how they interact with other grains and in their environment. Cylindrical or elongate grains have a tendency to roll, but we can also get imbrication. Think about elongate grains all lining up appropriately based on current direction. If we have a single direction current, your grains are probably going to be oriented parallel to that. Also, though, it depends on the environment. In a beach setting, you're going to see elongate grains orient themselves perpendicular to the direction of wave action. Equant or spherical or compact grains tend to behave differently than irregular shaped grains. Irregular shape have different pieces and processes sticking up in all different directions, which can allow for transport and initial erosion to happen in a different way than a compact grain. Tabular or ellipsoidal grains have a tendency to not transport quite as easily because they're hydrodynamically lower, and so they're harder to entrain to begin with. So when you're looking at sediments, make sure you pay attention to shape beyond just angular or rounded. Pay attention to the actual geometric shapes of the grains may have as well. Of course, grain sorting. Here, this is diagram 3.32, page 43 of your textbook. A standard sorting of clastic grains, where very well sorted would be most of these grains are about the same shape and about the same size and about the same degree of rounding. All the way then to the other end of the spectrum, very poorly sorted, where we have large and small grains, round and angular, and a variety of geometrical shapes in between. This is a good factor when figuring out maturity. Typically, our more mature bodies of sediments are going to be more on the well-sorted to very well-sorted side, and our poorly sorted to very poorly sorted usually lean more towards immature assemblages of sediments. And then finally, for our clastic rocks, we bring all of these things together. We bring shape and size and sorting, and we also bring in composition in many cases. So again, there's a lot of different petrographic classifications of different types of sedimentary rocks. Some of them are just as good as others. But for example, a conglomerate. This is going to be gravel-sized particles. They're usually rounded fragments. And the texture is rather coarse. So we're looking at gravel that's over 2 millimeters in diameter, each grain, for it to be considered a conglomerate. If it's a breccia, everything else is the same as a conglomerate, except we're looking at angular fragments. So the maturity is different. Notice we're not really saying much about sorting here, because you can have poorly sorted conglomerates and well-sorted conglomerates. It all just kind of depends on the environment. And we move down the ladder there with sandstone, siltstones, and shales, looking at the textures and what type of sediments. But notice we've said nothing here about composition. Composition is when we get to these ternary diagrams, where we can, what percentage of our sediments are rock fragments, so lithics, are what part of them are feldspars, what part of them are quartz, and everything kind of falls in between. So there's not only do we have that triangular diagram of lithics, feldspars, and quartz, but also looking at whether we're dealing with an arenite, a wacky, or some form of mud rock. So it's important to pay attention to what system you're using when you're classifying whether it's a clastic rock or even carbonates. And speaking of chemical and biochemical sediments and sedimentary rocks, we deal with these very different than we do with clastics. And we have a couple of different classification systems for carbonates, and they both work because they're telling you different things. The Folk's constituent classification of carbonates deals mostly with what kind of materials are in our carbonates and how are those carbonates formed in their fabric. So allochems, such as ooids, pelloids, and intraclasts, or limestone that's formed in situ, or even skeletal grains, so bioclasts themselves, shell fragments. These are our main allochems in limestones, but then when you look at what is holding them together, if it's cement with sparite, for example, we would have a biosparite if it's a bioclastic, or an oosparite, pellsparite, and so on. However, if we're dealing with macritic mud matrices rather than a cement, we would then say biomicrite. So you can have the same bioclastic skeletal grains, but are they held together by a sparry cement, or a macritic mud is going to tell you something very different. So the folk system deals more with what kind of allochems we have and what's holding them together. Alternatively, the Dunham system is based more on overall textural classification. We can still have some crossover a little bit with what type of materials are within, but this deals a little bit more with whether we're looking at a pack stone, which is lots and lots of materials kind of crammed together with a relatively smaller amount of cement or matrix. Mudstones are predominantly just macritic muds. And then we get all the way down to our grainstones, boundstones, and then crystalline carbonates, which is mostly recrystallized carbonates themselves. So we can use both of these together to tell us different things about our carbonate chemical sedimentary rocks. The Dunham system really kind of relies on whether there's mud or not. If you have carbonate muds with less than 10% grains, you'd call it a mudstone. a carbonate mudstone. If it's more than 10% it'd be of grains, then it would be a wax stone. And if it's mostly grain supported, it'd be a pack stone. So we have lots of grains, bioclast, for example, but there's a really, really low amount of muds, it'd be a pack stone. If there's no mud at all, and if there's no mud and it's entirely grain supported, then it would be a grain stone. If the original components are all bound together and there's no mud, that'd be a bound stone. And if you can't recognize any depositional texture, that'd be your crystalline carbonate. So looking at some of our biochemical and chemical sedimentary rocks and how they form, cherts, first of all, these usually form in nodules, layers, or beds, but they're all going to be formed of colloidal silica. And most of the time, cherts are forming diagenetically, but there are some exceptions where you have lots of siliceous microfossils, such as radiolarians and diatoms. You can form a chert from the breakdown of those. Also forming from hot springs, so these can also precipitate out. So most of our cherts are going to be diagenetically formed, but occasionally we can get them forming in other ways. Evaporites, another form of chemical sedimentary rock. These can include evaporites of sulfides, chlorides. In any case, the evaporation is exceeding precipitation. So three ways this can happen. First, the most commonly evaporation of seawater in an isolated area. Okay, so think of the Mediterranean or the Dead Sea. You can also have evaporation of fresh water in isolated lakes. These can also form evaporites just based on anything that's dissolved within that fresh water. Or the evaporation of temporary pans and groundwater sediments. So areas that are maybe seasonal, you can get evaporites forming there as well. Peat and coal, these are really the ultimate biochemical sedimentary rocks because they're made entirely of biochemical materials, pretty much pure carbon. When you have peat, that's a low-grade biochemical sediment, a mixture of partially decomposed plant remains with some possibly clastic material mixed in. This is going to be transformed through physical and chemical diagenetic alterations to give you your different types of coal, ultimately to anthracite. Ironstones and phosphates. Now, ironstones for chemical sedimentary rocks, these can be sulfides in the form of pyrite. You can get iron carbonates like siderite, iron silicates such as glauconite, and iron oxides like hematite. Most of these, with the exception of our oxides, are going to form under reducing conditions. Our phosphates, though, we have various types of calcium phosphate halides and hydroxides that we can be looking at. Most of these are going to form from the accretion of either ironstone or phosphate nodules in deep marine, deep sea environments, and replacement of other minerals that we also see happening in our slope and our shelf environment. So as I said at the beginning of this lecture, it's a relatively short lecture this week, just kind of a review of sedimentary rocks. I don't think we need to drone on much more about that. However, a couple of things for lab this week. We're going to be starting Project 2, and this is going to be done over a couple of weeks. So 2A deals with our core description of a section of core from the Illinois Basin. So now that we've reviewed different types of sedimentary rocks, we're going to start describing them in a stratigraphic context in the form of a core. So please print off Project 2A from Canvas and bring that to lab this week, and I'll explain the project, the first part of the project, in class. Just to remind you, though, that Project 1, what we did last week, our very basic review of sedimentary rocks, is due to Canvas by the time we have lab this week, so by Friday at 11:30 a.m. So make sure you have that done. It was a pretty short lab exercise, so it shouldn't have been too complicated, but make sure you do have that in. And make sure, again, you bring Project 2A to lab, and I will see you there. Thanks.